So our third and final example of just calculating delta S for a reaction involves P4 as a gas. That's just phosphorus, it's elemental phosphorus. P4 as a gas plus 6 H2s as a gas plus 8 O2s as a gas, producing 4 moles of H3PO4 as a solid. So this is a synthesis reaction, taking all these elements and making a compound. In our table, delta S0 for each of these substances. For P4, it's plus 163.2. For H2, it's 130.6. And for O2, 205.0. And for H3PO4, 110.5. This is joules per mole Kelvin. So we're going to calculate delta S for that reaction. Maybe pause here, try it yourself so you're not just watching me do the example. All right, so when I type this through, I'm going to use products. So we have 4 times 110.5. It's the only product, minus 1 times 163.2 plus 6 times 130.6 plus 8 times 205.0. All in joules per mole Kelvin. So I dig out my calculator. 4 times 110.5 minus 163.2 minus 6 times 130.6 minus 8 times 205. So go ahead and type that through. Make sure you get an answer for it. I get 2144.8. Minus 2144.8 joules per mole Kelvin. So this one was negative. The enthalpy was negative. And we should have expected it to be negative because we took elements and turned them into a big molecule. Small molecules becoming big, gases becoming solids, all that stuff. It double dips. So you get a big negative, that's a very large negative entropy for a reaction. So there's much more disorder on the reactant side than the product side because it's negative and a very large magnitude number. Okay? So this should give you an example or 2 or 3 about how these delta S problems go. And if you were okay calculating delta H last semester, you should be okay calculating delta S this semester because they really don't work that much differently. All right, when we come back, we're going to look at feeding H and S into the same system of equations and coming up with an entropy and enthalpy driven decision on spontaneous or not spontaneous.